Electrolyte Solutions. Milliequivalents. So this unit of measure is related to the total number of ionic charges in solution. So it takes note of the valence of the ions. In other words, it is a unit of measurement of the amount of chemical activity of an electrolyte. So for a given chemical compound, the milliequivalence of cation equals the milliequivalence of an ion, equals the milliequivalence of the chemical compound. Okay. So here is the usual reference range of some electrolytes. Okay, so sodium, potassium, calcium, magnesium chloride, carbon dioxide, and phosphorus. So in your other subjects, you will be taught about the abundance of these electrolytes. So you will know what the major extracellular cation is, or what the major intracellular anion is, and so on. So you just take note of these. Okay, so milliequivalents. So here is a summary of the equations that can be used in solving for this. So to convert milligrams to milliequivalents, we use this formula. To convert milliequivalents to milligrams, we use this formula. And to convert milliequivalents per milliliter to milligrams per milliliter, we use this formula. So in the formula, there are common terms like valence, atomic formula or molecular weight, and so on. So valence is determined by the number of electrons that an atom can lose, add, or share. So later, I will try to teach you how to determine the valence of the compounds. The atomic formula or the molecular weight of a compound is determined by adding the individual molecular weights of the elements involved. Okay, so later you will understand how to compute for this. So in this example, what is the concentration in milligrams per milliliter of a solution containing 2 MEq of potassium chloride per milliliter? So first, let us determine the molecular weight of KCl. So KCl has two elements, right? We have K or potassium and Cl or chloride. So we must be familiar. I mean, we may not memorize, but we should at least be familiar with the molecular weight of each element. So potassium has around 39 or 39 grams per mole, while Cl has around 35 grams per mole. So the more accurate molecular weight for KCl is 74.5. Okay, so the equivalent weight is 74.5. Now, to determine the concentration in milligrams per milliliter, we can use this formula. So 1 MEq, or 1 milliequivalent of KCl, is equal to 1 over 1000. So 1 here is the valence. So we got this by determining the oxidation state or the oxidation number of potassium. So potassium has an oxidation number of positive 1. Therefore, you will use 1 as the valence. Okay, so you should also be aware and familiar with the oxidation states of the different elements. Okay, so again, we have 1 over 1000 times the molecular weight, which is 74.5. So the answer is 0.0745 grams. Okay, now this unit can be, since this is in decimal form, we can convert it to milligrams to be more workable. So 1 MEq of KCl is equal to 74.5 milligrams. So since there are two milliequivalents being asked, we can multiply this by 2. So we'll have 149 milligrams per ml. So we may also use this equation. So we have this or this. So we have the milliequivalents per ml times the atomic formula or the molecular weight over the valence. So the answer is 149 milligrams per ml. Okay, so this seems to be more, this seems to be easier. Okay, so you just memorize this formula. So another example, how many milliequivalents of magnesium sulfate are represented in 1 gram of anhydrous magnesium sulfate? So first, let us determine the molecular weight of magnesium sulfate. So magnesium has a molecular weight of 24, sulfate has 32, and oxygen has 16. But since 16 has 4 atoms, you should multiply 16 by 4. So the total would be 120. So the equivalent weight of magnesium sulfate is 60, since the valence of magnesium sulfate is 2. So how did it become 2? So if you recall your lessons from inorganic chemistry, sulfate has an oxidation number of -2, and so that means that magnesium has an oxidation state of +2. So since it is 2, it will also be its valence. So 100 divided by 2 is 60. So to compute for the mole equivalent of magnesium sulfate, we will have 1 over 1000 times 60 grams, which is the equivalent weight of magnesium sulfate. So we will have 0.06 grams or 60 milligrams. So since 1 gram of magnesium sulfate is 1000 milligrams, 60 milligrams is equivalent to 1 MEQ. That would mean 1000 milligrams would be equivalent to 16.7 milliequivalents. Okay, so again, you can use the equation here, stated here. Okay, so let's have more examples. So a person is to receive 2 milliequivalents of sodium chloride per kilogram of body weight. If the person weighs 132 pounds, how many milliliters of a 0.9% sterile solution of sodium chloride should be administered? Okay, so first of all, again, determine the molecular weight of sodium chloride. So sodium is 23 and chloride is 35.5. So we have 58.5. So the equivalent weight is 58.5 as well, because the valence of sodium is +1. Okay, so 1 milliequivalent of sodium chloride is equal to 1 over 1000 times 58.5 grams is equal to 0.0585 grams. And so that means if we need 2 milliequivalents, we will have 0.117 grams. Okay, so we now have the corresponding weight of sodium chloride in 2 milliequivalents. Okay, so next is we compute for the weight. So again, since 1 kilogram is equal to 2.2 pounds, 132 pounds is equal to 60 kilograms. Okay, so because this person is to receive 2 milliequivalents of per kilogram, then 2 MEQ or 0.117 grams times 60 is equal to 7.02 grams of NaCl. Okay, so because 0.9% sterile solution of sodium chloride contains 9 gram of NaCl per liter, then 9 grams is equal to 1000 ml. So 7.02 grams is equal to 780 ml. Okay, so how did it happen? Let's go here, 0.9%. Okay, so 0.9%, there's percent, so that means there is 0.9 grams per 100 ml. Okay, but since what we're looking for, 0.9 grams per 100 ml, which is also equal to 9 grams per 1000 ml. Okay, so do not be confused with that. So they are only equal. They are equal. Okay, so ayun, you just plug in the values, 9 grams per 1000 ml, and we got this 7.02 from here. because we will find the equivalent volume. So the answer is 780 ml. So if it is not that clear, you try to solve it on your own, okay? So you can have a better grasp of how to solve it. So next topic is millimoles and milliosmoles. So to calculate millimoles, a millimole is a thousandth of a gram molecular weight of a substance. So 1 millimole is equal to the molecular weight in grams over 1000. While to calculate milliosmoles, it is a thousandth of an osmole. So when substances do not dissociate, the numbers of millimoles and milliosmoles are the same. So there are 2 milliosmoles per millimole for substances that dissociate in 2 particles, and 3 milliosmoles per millimole for substances that dissociate into 3 particles. Okay, so take note of that. So milliosmoles is equal to the milligrams of drug times 1 millimole of a drug over the molecular weight. So here is an example. A solution contains 5% of anhydrous dextrose in water for injection. How many milliosmoles per liter are represented by this concentration? So the formula weight of anhydrous dextrose is 180, and 1 millimole of anhydrous dextrose, which is 180 milligrams, is equal to 1 milliosmoles because it does not dissociate further. Okay, so like stated a while ago, the millimoles and the milliosmoles would be equal. So since 5% of the solution contains 50 grams or 50,000 milligrams per liters, 50,000 milligrams divided by 180 is equal to 278 milliosmoles per liter. So we can also solve this by using dimensional analysis. So we have 50,000 milligrams over 1 per 1 liter times 1 milliosmole per 180 milligrams. So the answer is 278 milliosmoles per liter. So you can take note of the formula that is written below. So we now are at IV infusions, parenteral admixtures, and rate of flow problems. So let us first define IV infusions. So intravenous infusions are sterile aqueous preparations administered intravenously in relatively large volumes. So when we say intravenously, they are administered directly into the veins. So the functions are stated below. So when are IV infusions administered, or what are they for? Aside from IV infusions, we also have IV injections. So large volume parenterals, they are those that contain 100 to 1000 ml of liquid. So they are administered by infusion. So there are also small volume parenterals which contain up to a maximum of 100 ml of liquid. So they are packaged into ampules, vials, and pre-filled syringes. Okay, so IV infusions also involve continuous infusions and intermittent infusions. So differentiating the two, continuous infusions are large volume parenterals with or without drugs and are run into a vein uninterrupted for a specific time duration. Okay, so the keyword is uninterrupted, while intermittent infusions are those administered during scheduled periods. An IV push, on the other hand, is also called IV stat or IV bolus. So it is a relatively large dose of medication administered into a vein in a short period or in one immediate shot. Okay, so rapid injection in an emergency or critical care situation, so that is an example of IV push. So they intend to quickly control heart rate, blood pressure, cardiac output, respiration, or other life-threatening conditions. So it depends on the precise calculations of those and rate of administration. IV admixtures, so they are preparations involved in the addition of one or more drugs with or without additives to large volume parenterals. Example, sodium chloride injection, dextrose injection, lactated ringers injection. So additives include electrolytes, antibiotics, vitamins, or trace minerals. So regarding rate of flow of IV fluids, on medication orders, the physician specifies the rate of flow of IV fluids in ml per minute, drops per minute, amount of drug per hour, or more frequently in the approximate duration of administration of the total volume of the infusion. So here are problems for you to practice on. So how many grams each of dextrose and sodium chloride are used to prepare a 250 ml bag of D5 1/2 NS for intravenous infusion? So first, what is D5 1/2 NS? So it is 5% dextrose in half normal saline solution. So what is asked is the number of grams each of dextrose and sodium chloride. Okay, so since we know that the infusion should contain 5% of dextrose and 1/2%, 1/2 of normal saline solution, the computation is as follows. So the volume is 250 ml. So to get the total amount of dextrose, we only need to multiply it by its concentration. So since it is 5% dextrose, 5% weight per volume, we have 5 grams of dextrose per 100 ml. And 5% is also equivalent to 0.05. So the shortcut would be to simply multiply 250 and 0.05. So the answer is 12.5 grams. Next, for the 1/2 normal saline solution, you would expect that it would be 0.5, but no, it is not. Why? Because a normal saline solution is 0.9%. Okay, so and what is half of 0.9? It is 0.45%. So we will do what we did with the computation for dextrose. We can divide 0.45 by 100 to get 0.0045, and we multiply this to 250 ml. And we will get 1.125 grams of sodium chloride. Okay, so be careful with using the proper concentrations for the infusions. Okay, for the other problem, you may solve this on your own. Okay, so next problem. A medication order for a patient weighs 154 pounds calls for 0.25 milligrams of amphotericin B per kilogram of body weight to be added to 500 ml of 5% dextrose injection. If the amphotericin B is to be obtained from a constituted injection that contains 50 milligrams per 10 ml, how many milliliters should be added to the dextrose injection? So again, this is one of those very long questions which require only a little to solve, okay? So it's not that complicated. So first, we try to convert the given weight of the patient. So 154 pounds to kilograms, we will have 70 kilograms. Next is to identify the total amount of drug needed by the patient. So since the dose calls for 0.25 milligrams of amphotericin B per kilogram of body weight, we simply multiply 70 kilograms times 0.25 milligrams. So we will have 17.5 milligrams in total. Now, the constituted solution contains 15 milligrams per 10 ml. So if we only need 17.5 milligrams, how much volume is needed to be administered? So since the solution's concentration is 50 milligrams per 10 ml, we plug that in the equation. So 50 milligrams per 10 ml. Okay, and since we only have 17.5, here we will place X. So if you compute this, it would be 7.5 times 10 divided by 50. The answer is 3.5 ml. Okay, so a more systematic way is by using dimensional analysis. So we have 154 pounds times 1 kilogram over 2.2 pounds. So we cancel pounds. Next, 0.25 milligrams per kilogram. We cancel kilograms. And lastly, we multiply the constituted solution concentration, which is 50 milligrams per 10 ml. But to cancel the milligrams unit, we should uh, place the reciprocal of the given. So we now have 10 ml per 50 milligrams to cancel milligrams. So the answer is 3.5 ml. Okay. So this is another problem I advise that you do on your own. So you just need to go step by step, and hopefully you're able to understand how they arrived at the answer of 21 drops per minute. Okay.